Swayam Prabha. Digital India. Educated India.
What we will do to start with is, let us consider a vector, let us say a vector like this. So, let us say this is a vector r. Okay. I am just going to represent this as that vector. Let us say this is point A, this is point B. Okay. So, this is point A, this is point B. Now, if I have to find out the change in this vector, let us say this vector has a magnitude and a direction. If I have to find the change in this vector, what all changes are possible? The changes that are possible are in the magnitude and in the direction, right. So, this can change and this can change, alright. So, when I take the time derivative of the change in a particular vector, it will involve product of the time derivative of the magnitude change and the time derivative of the directional change. Okay. Most often than not, since we most of the times think in terms of scalars, this concept of derivative of the vector becomes difficult. Okay. So, let me just introduce that particular concept first, so that it is easier when we derive motion of rigid bodies. Okay. So, this is a 3-dimensional vector. Okay. Okay, let me just put it like this. Okay. Now, if a change occurs in the direction only, let us look at what happens, so that we can proceed forward to take the change with respect to the magnitude. So, let us say it is something like this and it has shifted its direction, okay, arbitrarily in a particular direction. One thing that we find is there is an initial direction and there is a final direction and there is an angle between them. So, there is one like this, let us say one like this, okay, which is not exactly out of plane, but a plane that is something. You know that there is a plane that can pass through the changed vector and the original vector, alright. So, let us say on that particular plane, if I take that particular plane, okay, rotate it and make it this blackboard, then what I would see is it would be like this and it would have changed to something like this. Okay. Now, let us just retain A to be at the same place and look at the change in B, alright. So, it makes it easy for us to understand. Okay. Once we have a visual picture, then it is easier to comprehend what happens to the time derivatives. Okay. So, let us say after a gap of delta t, I notice that this vector has now shifted direction to something like this. Okay. So, let me just draw that. Notice that I have assumed that there is no change in the magnitude, just to start with as an assumption. Okay. So, it would have gone from B to B prime. You agree with me? So, initially let us call this as RAB, it has become RAB prime. Okay. When I put a line at the bottom, it means a vector, alright. So far so good. Now, I need to find out how much changes occurred in this vector. Okay. The magnitude has not changed or the direction has changed. So, naturally if I have to find out the change, it is the changed vector minus the original vector will give me the changed vector over delta t, right, and let us call that as delta r, okay, delta r. Okay. So, what would be delta r here? Naturally RAB plus a vector like this will give me RAB prime, and therefore, this should be delta r. So far it is okay, no problem. And what is this angle? Let us take this angle to be some delta theta. mind you, we will use this in order to find out the time derivative. Okay. Now, limit as delta r by delta t at delta t tends to 0 will be nothing but limit as this tends to 0, correct. This is okay. So, limit as delta t tends to 0 r a b prime minus r a b vector by delta t, perfectly all right. Okay. Now, how do I find out the, so in this particular case if I look at this delta r again has a direction and a magnitude. Let us look at the magnitude. What would be the magnitude of this delta r vector? Can I find out? That is the question I will ask. I know that this is a delta theta sweep that has occurred about A, and I know delta theta is small because I am taking a limit. Okay. So, for small delta theta that has occurred over delta t, can I find out this, since the lengths of RAB and RAB prime are the same, it is equal to this one of the lengths times delta theta. Okay. So, let me just call that as R times delta theta. All right. And what is this R? It is the magnitude of the vector for which we are finding the time derivative. Okay. So, it is easy to find out the magnitude. How about the direction? Okay. Let us look at this particular plane. Is this particular, any vector in this particular plane, can I say is perpendicular to a vector that is outward normal to this plane? The answer is yes. So, it is perpendicular to this r, it is perpendicular to this delta r, all right. Now, when we found this particular r times delta theta, we took this to be tangential to RAB, or in other words this was perpendicular to RAB. So, the fact of the matter is, number 1, delta r vector is perpendicular to outward normal, let me call it as n of the board, all right. It is also perpendicular to RAB. Do you agree with me? Okay. What am I interested in now? I am interested in finding out only the direction because I know the. So, if I need to find out the direction, let me just put a cap over here just to indicate that I am looking at a unit vector along this direction. Okay. So, let me call the one that is perpendicular as n. Let us call this as, let us say, m vector without loss of generality. So, what I am basically saying is this is perpendicular to m cap. When I put a cap, it means it is a unit vector. Okay. If this is the case, what do you know about the direction of delta r? What would be the direction? Very simple. If I know a little bit of vector algebra, it should be related to the cross product of these two. All right. N cross m will give me delta r. With the consistency in direction, I should be able to find out, right. So, if I take n and then cross it with m, I should get delta r, and therefore, I will say delta r cap is equal to n unit vector along the perpendicular direction crossed with m. So far so good, no problem. So, let us put them together. I know the magnitude, right, I know the direction. Now, what is delta r equal to? It is equal to delta r magnitude times delta r direction. Okay. Putting them together, it is del r delta theta times n vector cross m vector. Any questions on this? Okay. Now, we will proceed to the time derivative. All right. So, let me write this as limit as delta t tends to 0. What is this? I am going to take that, which is r times n cross m times delta theta by delta t. Just substituting this expression over here. Okay. Limit as delta theta by delta t will give me theta dot. Okay, and therefore, this will be r theta dot n cross m. Is this clear? Okay, so let me call that as r dot of AB. Okay, I can just drop this r dot here and just say r instead of r dot AB, I will just say r dot is equal to r theta dot n cross m. Okay, we are not done yet. We just need one more step so that we understand what is happening here. Okay, so far so good. Let us just look at it again, and therefore, I have r dot. What is r dot? It is the derivative of the vector r. Okay, that is equal to, borrowing from this, it is r theta dot n cross m. What is this m here? What is this m? This is the direction along r. What is this? Magnitude of r. If I combine these two, it is nothing but theta dot n cross r. All right. Now, what is theta dot times n? As I told you earlier, when I had a 3-dimensional vector and it changed position, I took the plane of that plane that is formed by the two vectors to be this vector, right, and therefore, the rotation is actually occurring along an axis that is perpendicular to this plane, okay, and therefore, this is nothing but angular velocity, the velocity with which it is rotating about an axis, and therefore, this is omega cross r. Okay. One important thing that I have to understand is I have pivoted about this point A. That is an important thing to understand. The reason is, supposing the point is somewhere else, then I will have to rewrite in a different fashion. But to give you an idea that r dot involves omega cross r is an important result that we will be using over and over in kinematics of rigid bodies.